this example is month. So detailed data, the most detailed data you can see is month, and most summary data, the data is year, right? So in simple word, I can see the data summary level, this is quarter, and I can go to detail level for each quarter and month. What is user view for the hierarchy? User always want to see the detail and summary information, right? In this report, what is the processing engine behind this? It could be SBase, it could be RDBMS. I'm looking at the revenue for each quarter and each month revenue. I would like to see the summary information, the total revenue for each year. This is each quarter revenue, right? Quarter 1, quarter 2, quarter 3, quarter 4. I would like to see the total year revenue or monthly revenue for quarter 1. So quarter 1 monthly revenue, this is a monthly revenue for quarter 1. This January, February, March. I would like to see the daily revenue for January. This is daily revenue for January. So depends upon my hierarchy, business can see the detail or summary data. As a part of my analysis, we should incorporate this thing. Sometimes requirements are pretty straightforward. So hierarchy is quite visible. Like in this example, we can easily identify the geographical hierarchy, which is country and city. We can also easily identify the product hierarchy, which is product line. Under product line, we have got product family. Under product family, we have got product category and name. We also have a store hierarchy, store type. Each store type has many managers. Each manager owns multiple stores. So this is a hierarchy. So sometimes your requirements are pretty straightforward and you can figure out the hierarchy. Sometimes by analyzing the requirement, you can identify the hierarchy. So this is an example of your geographical hierarchy. This is another example of hierarchy where the product has been chosen. Now how the multi-dimension look like, how the hierarchy look like in multi-dimensional view. Okay, the multi-dimensional data is present in terms of cubes. Therefore we use a term called interchangeably cube. And the same presentation, if you do it in Excel sheet, it would like this. This is two-dimensional cube. The same presentation I am doing in Excel sheet. So this is three-dimensional cube. One dimension is time. Second dimension is province. And third dimension is, in this example it is product, in my example is a sales manager. When you organize this and graphically, it looks like a cube. And this cell, intersection of one product, 1 month and one region, this is a one cell, small cell. This is the smallest unit where data is stored. So this is a cell which is intersection of time, province and sales manager. The data is stored at this point. This cell representing this intersection. Okay, in a multi-dimensional view, how the the hierarchy look like. Now, if you look at this example, the hierarchy might look like this way. This is the data for January. This is for February, and this is for March. And this total data is for quarter 1, right? The sum of January, February, March is a quarter 1. This is total data for quarter 1. Similarly, I would have another data. there would be another cell like quarter 1, there would be quarter 2 as well. This is quarter 1 and this is quarter 2. And the sum of all quarter 1 and quarter 2, this would be half year. So the hierarchy is half year. Under half year we have quarter 1. Under quarter 1 we have January, February and March. This is my hierarchy in this example. Half year, quarter 1 and Jan. This is how we represent the data. Intersection with sales. So this data is going to be read sales intersection with the month of January, with month of quarter 1 and half year. So what is my quarter 1 sales? Sum of January, February and March, 3000. So this is the lowest level of granularity, which shows 1000. Next level of granularity, quarter 1 sales would be sum of January, February, March, 3000. So similarly I would have for February and March. So January, February, March data aggregate to become quarter 1. All quarter data will aggregate to become half yearly. So your half yearly would be 6000. Half yearly would be sum of this April, May and June. This is how S-based logical multidimensional database organize the information this way. So that's called a multidimensional view of information. We can cut one piece of the cube and focus on certain area. Okay, so this is my multidimensional cube. When I cut up one piece of it, when I cut one piece versus another piece, what does this two cell talk about in terms of business? Total revenues received by sales manager John under store type online sales versus total revenue received by Mac under store online sales by Mac. So we are comparing two sales manager sales. Similarly, if I take another example of this cube, so if you cut the cube from different pieces, it brings a certain meaning. You take this piece of the cube versus this piece of the cube. So you are comparing quarter 1 sales versus quarter 4 sales for John under online sales. If you compare these two piece of cube, what does it say? Quarter 1 sales done by sales manager John under online sales versus direct sales. So you cut cube in different pieces and it might bring a certain business meaning for you. That's the beauty of your multidimensional database. Okay, we discussed about star schema in the last class. I'm going to continue with this part. In a star schema, we discuss about dimension, facts and organization. There's another version of star schema called snowflake. Okay, I'll show you star schema and snowflake both in one go. Okay. Okay, I'll look for some simple example. Okay, this is my star schema. This is my star schema where one fact is surrounded by multiple dimension table. each dimension is denormalized. When we normalize any one of the dimension and split across two dimensions, this becomes a snowflake. Right? This star which has got one dimension, the dimension split into two dimensions, this becomes snowflake. Therefore, we call snowflake model is normalized version where each dimension or any one of the dimensions is normalized. This becomes a snowflake model. Where any one of the dimensions is further normalized. This is called a snowflake model. Now, a snowflake model is designed. The star and snowflake model both have a different requirement. The snowflake model is designed in order to support insert and update operation. The more normalization we have, the less duplicate data we have, right? So, I shown you in the last class we go towards normalization and denormalization. What are the benefits? Important of snowflake is that in one line, if we can draw the reference, star schema, fast query performance, not designed to support insert, update, delete operation. Support means it is technically possible, but there are a lot of difficulty associated. There will be duplicate multiple ways to multiple places to delete the data. Large number of duplicate records. Snowflake relatively slow query performance, support insert, update to some extent, and relatively less duplicate records. You see there are large number of duplicate records I have. Right? There are large number of duplicate records because the data is not normalized. I denormalize everything I put into one table, one Excel sheet. Therefore, large number of duplicate records. The preferred model for Hyperion SD is a star schema. So we suggest our data modeler to convert this star schema, snowflake